Now in this more practical video I will show you how to compare two voltage levels to each other using an operational amplifier and how to switch an LED on and off depending on the result of the comparison. First we're going to quickly review the operational amplifier and comparator equations, or the operation modes, which we have discussed in the last video, and then we're going to simulate the circuit over on Tinkercad to see how we can set up such a circuit on an actual breadboard. Now in this diagram here you can see the basic idea which we're trying to implement here. We have the operational amplifier, we have the input voltage here on the so-called non-inverting input, which in the diagram here is the blue curve, which has a fluctuating sinusoidal signal. We have a constant voltage being fed to the inverting input here, which corresponds to the red line, and as soon as the two are of equal size, or if the blue curve exceeds the red curve, the output pin of the operational amplifier goes to high, which is the operating power here, the operating voltage supplied to the rails of the operational amplifier. Now we want to simulate this switching circuit in a simulation and use it to trigger on and off an LED which is powered by a transistor. And in case you're wondering why we need a transistor, we don't actually need it in order to simply switch on an LED, but we can use the operational amplifier to trigger a transistor-based switching circuit which can switch on and off much more than a simple light-emitting diode. So this lays the groundwork for switching on and off stuff, let's say a motor, a relay, which can be done with an operational amplifier in this switching stage. Now let's head over to Tinkercad to see how we can construct such a thing. Now let's take a look at this circuit here on the bottom. Maybe you recall this from the last video, which we have looked at on using the transistor as a switch. The transistor here gets a signal over its base, and based on this signal, the collector-emitter path becomes either conductive or non-conductive, and if it's conductive, this LED here gets power and lights up accordingly. So if this signal here, which enters the base here across this transistor, has a sufficiently positive voltage, then the LED lights up. And if we start the simulation, you can see here that we have a current flow of 21 milliamps through the LED, which is a little bit too much here, but nonetheless it's still well within the operating parameters of the simulation here. So 20.2 milliamps is perfectly fine for operating an LED. Now what we want to do is we want to use this operational amplifier on this additional breadboard here up top as a switch in order to trigger this signal here, which now enters the transistor from the power supply. Let's stop the simulation, let's remove this signal line here, and let's properly connect the operational amplifier. First let's connect the positive power supply, which is this pin here. Let's draw a connection to this connector here. Let's angle it a little bit to increase the overview over our circuit here. And also let's change the color to red to make it clear that we have a positive power line. This connection here, power minus, this leads to the negative power supply. And in order to also get this fed into the power supply, let's draw it down here and enter it here and color it in black to make it clear that it's a negative power supply line. Okay, here are the inputs, inverting and non-inverting, and above here this is the output. So the output is going to trigger the base, and this is why I'm going to feed the output now into the same spot where previously we had the signal from the power source, just as you can see here now. And let's recolor this a little bit and, for example, change it to orange to make it clear that it's a positive signal which we are expecting here. And now we have to feed something to the input pins. First, the non-inverting input. This is going to simply get a power signal from the power supply, but we could also use a sensor for this here, which is something we're going to do in later videos. And now, as we have learned about the operational amplifier as a comparator, the output is going to be positive as soon as the power difference, the voltage difference between the non-inverting input and the input is positive. The output is going to switch on. And this is why we need to connect the inverting input here with the negative power supply. Let's recolor this appropriately, and now we feed 9 volts to the non-inverting input, we feed 0 volts to the inverting input. This makes the difference positive, and this is why the output should switch to on and pull it to 9 volts, which then should feed power to the base of the transistor. Let's see if this works. And as you can see, clearly works. We have a little bit more current flow here, 22.1 milliamps, but the principle is the same here. And as soon as I change, for example, the cabling, let's say connect the 9 volts to the inverting input and the 0 volts to the non-inverting input and start once more, you can see that the LED stays switched off simply because the voltage difference between the input here is negative. And this is a way to use the operational amplifier as a means of comparing two input signals, and in case of a positive difference, switch on the output and then, for example, trigger a transistor as a switch, which could then switch on an LED or something else, for example, a relay or a motor.
Let's take a look at the circuit which we have just seen in the simulation. This is the centerpiece, the heart of the entire circuit. This is the operational amplifier, the OpAmp, and if you look very closely, it's hard to see in the light, but it says LM358N. This is the type ID of this operational amplifier here, and if you look it up on the data sheet, you will find that this pin here is for positive power, and this one is for negative power connection to the battery, and the other ones on the upper side and on the lower side lead to two separate operational amplifiers. That means inside this housing there are actually two op-amps which we can use. In this circuit, however, we are only using a single one, and this single one is connected to the lower side. Now let's take a look at all the components you can see here before we connect it to the battery. First of all, the positive power supply, this one here, is connected to the upper power rail, which is going to hold the positive connector of the battery. Let's put it in here. And once current flows, this ensures that the current only flows into a single direction into the operational amplifier, because if I confuse myself, for example, if I should not think properly and by accident connect the negative power connector to this power rail here, then this LED will this diode here, it's not an LED, it's a diode. This diode will save the life of the operational amplifier by not letting the current through in the wrong direction. So this is the purpose of this diode here. It's for safeguarding the operational amplifier. Now let's connect the red connector back again here. On the other side, we have the output pin of the operational amplifier. It's in the lower left corner, and this is connected to this resistor here, which limits the current flow from this output pin to mass. And mass is going to be connected to the lower end here. And also in between this resistor here, we have this diode, which indicates whether the output pin is activated or not. On the lower right side, you can see this pin here, which leads directly to ground, to the negative terminal of the battery. And this is all there is needed to connect this operational amplifier. And these two pins here at the bottom, these are used for comparing two signals to each other. And now let's power up, before we connect these to something, let's power up this whole circuit here. And as you can see, as soon as I connect the negative terminal of the battery to the lower power rail, the LED lights up. The reason why this is the case is that this operational amplifier has a significant gain. This means even minute differences between the two entrances are amplified by a factor of 10 to the power of 5, 10 to the power of 6. So a very small difference already brings this operational amplifier and its output into saturation, which means it outputs the maximum amount of power it can output, or the maximum voltage, and this is limited by the supply voltage, in this case 9 volts from the battery. And now let's connect the two inputs of the operational amplifier to actual voltages somewhere on the board. Let's connect, for example, the left one using a yellow cable to the plus 9 volt power supply, and the other one by using a black cable here, for example, to the negative terminal of the battery. As you can see, the light goes out, and the reason behind this is that the differential measured by the operational amplifier is now at minus 9 volts. We have connected these two connectors in such a way that the difference between input 1 and input 2 is negative, and this means the operational amplifier switches off its output, and this is why the LED goes out. And as soon as we pull this one out here, the difference is again very close to zero, and even if I put it up here, it's almost the same, but with a minute difference in between the two, but this is still enough to have the output pin at full power. In practice, in one of the next videos, we will connect these input pins to a sensor and a Wheatstone bridge, which is used in order to generate comparative voltage values based on light intensities. And this is going to be a slightly larger circuit where we use a comparator, an operational amplifier as a comparator, in order to compare the ambient light to a reference value. And this is going to be very useful in order to switch on the light as soon as the ambient light on the sensor falls below a given threshold. This is one of the primary use cases of a comparator. Compare two voltages and trigger an output once it's above a certain threshold.
That's it for this video. If you have any questions, drop them into the comment section down below. And now I wish you a nice day. See you next time here on The Fearless Engineer.